kind of like it did in this problem set, or is it, does it have this kind of bubble effect where the cumulative effect of advertising builds up and then starts to die off, kind of peaks? And the reason we want to do that is because we can get this advertising duration. Over how long does the effect of advertising last? When is the peak effect? We can answer those kinds of questions. So in essence, today we're going to do the bubble. The bubble's the easier of the two. And that's it. So as nasty as the stuff that we're going to look at looks, all we're trying to do is impose some structure, impose some structure on the lag coefficients so that if we think it's going to have a bubble effect, we can force it to look like that and get that nice look. Just as if we think it has that decaying effect, we're going to force it to look like that and get that nice look. So that's what we're going to do. And there it goes. This is called a polynomial lag, or it's also sometimes called an almond lag, after the woman who I guess first has a published use of it back in 1965. All right. So what did she do? All right. So we're imposing structure on those lag coefficients. And remember the problem with the lag coefficients. This thing called multicollinearity. And again, what multicollinearity does is it creates imprecision in our coefficient, in our regression coefficients. That creates doubt in our confidence in those coefficients. So we know they're imprecisely estimated, so we're not real comfortable with them. So we're going to try to impose some lag structure. So what we're going to do is pretty easy, theoretically. We're going to impose this structure on the lag coefficients where I is the number of lags and R is the degree of the polynomial. So I is the number of lags in our model, which we're still going to have to use the Akachi and the Bayesian criteria. We're still going to have some guide on how many lags we've got to use. And then R is generally going to be a polynomial of order 2, a quadratic function. Because remember what polynomials look like. Right? That's a quadratic. A cubic is going to look like that. And we don't think advertising is going to have a cubic shape. But kind of in general, the generic form is something like that. And this might help, it might hurt, is to just kind of go through the math of this. Okay, so again, we have to select the degree of the polynomial, which is going to be a quadratic 2, and the lag length, which we have no idea until we get the data and start running some tests on it. All right. So let's assume that we choose a third degree polynomial and a lag length of 4 periods. In essence, we're going to construct coefficients according to that formula. So what does that formula tell us? It tells us, okay, so here's our unstructured distributed lag model. So this is the problems that we just finished. We ran this regression, we graphed the coefficients. And it's unstructured. That's why we got that wacky, went down, went down, went up again, then went down, and that's where we get that wacky stuff. There's no structure imposed on this, and we know that some of this spikiness might be caused by multicollinearity. So hence it's unstructured, and again we know it's estimated imprecisely. That imprecision creates doubt in our minds on people forget, and they also remember a period later, then they forget again, and all those other things. So it's a really hard story to tell when you have these unstructured distributed lag models. But like I said, they're probably used 90% of the time, 95% of the time. but we've already seen the results. They just come out awkward. It's hard to tell those stories. All right, so we're going to impose, so given that we're assuming a third-degree polynomial and a 4-period lag, we're going to take each of our coefficients from our lag model, beta 1, beta 2, beta 3, or beta 0, beta 1, beta 2, beta 3, and we're going to impose this mathematical structure on it. Again, I is the number of lags, R is the order of the polynomial. So it's, remember we said it's we're assuming a third-degree polynomial. So hence we got I to the 1, I to the 2, I to the 3. All right. Where I is the lag length. So we're literally going to take the lag length and raise it to the first, second, and third power. I mean, it seems kind of silly. So in our first period, I'm sorry, for beta 0, the coefficient of xt, for beta 0, which is the coefficient of xt, what's the lag length on those, in that coefficient? What's the lag of xt? 0, exactly. So we're going to take 0, raise it to the 1 power. We're going to take 0, raise it to the second power. We're going to take 0, raise it to the 3 power. What's that all going to equal? Boom. We're going to end up with the constant, because everything else is going to 0 out. We're going to take the coefficient on xt minus 1, which is the 1-period lag. So we take the lag length, which is 1. We raise it to the first power, raise it to the second power, raise it to the third power. And again, we're going to have to actually do this mathematically. Data doesn't do this for us. 1 to the whatever is always going to be 1. So beta 1 is going to equal that. We're going to take beta 2, which is the coefficient on the 2-period lag advertising. And again, we're just going to take 2 to the 1 power, 2 to the 2 power, 2 to the 3 power. And we're just going to do the math. And that's going to be 2, 4, and 8. We're going to take beta 3, which is the coefficient on the 3rd-period lag value of advertising. 3 to the 1, 3 to the 2, 3 to the 3. Do the math. And we get that. We have a 4-period lag model, so we got one more. And that gives us, again, 4 to the 1, 4 to the 2, 4 to the 3. That gives us 4, 16, and 64. So we're imposing this cubic polynomial on a 4-period lag model. And we're going to take these coefficients. Any questions? Because you're going to have to actually do this. You're going to have to actually do the math here. I think it's sophisticated math. Just 2 squared. Yeah, so it's. But we got to do this by hand. But it'll take you. How long is it going to take you to write a code for 2 squared, 4 squared? Okay, so I'm going to switch slides, but I'm going to take that same slide and it's up there now. So that's that circle part we just finished. All right. Then we're going to substitute those.
That's not right.
Back into our model. We're going to substitute. I need my laser. We're going to substitute these things back into our betas here. So beta 0 is going to be gamma. beta 1 is going to be that entire thing. So, does that make sense? We're going to substitute gamma 1, gamma 2, gamma 1 plus gamma 2 plus gamma 0 plus gamma 1 plus gamma 2 plus gamma 3
Collect like terms.
into beta 1, into there.
Like terms.
So that's substituting for beta 0.
That's hard.
That's substituting for beta 1. That's substituting for beta 2. That's substituting for beta 3. And that's substituting for beta 4. Don't blame me, it's all that woman's fault.
Almond.
Yeah. blame her.
Never eat almonds again.
I wonder if she's still alive. Actually, I don't even know. All right, so we're not quite done yet. All right. Now we're going to construct this new variable called z. Remember, in the end, we want that parabola. We want that sucker. And we know that the formula for that, for example, if this was just algebra or whatever class we cover this is just going to be what is this? ax squared plus bx plus c, right? That's a quadratic equation. That'll construct a graph of this will look like that, or upside down or something like that. So obviously this gigantic equation looks nothing like that. So what we're going to do is we need to make this thing look like that by constructing this new variable z. So in the end, this is what we want. We want to get this, and then we're going to run this one in Stata. Stata is going to run this regression. So we're not going to run that big, ugly, nasty thing, but we got to do all the math to get that big, ugly, nasty thing to look like that. Then we can regress this. Reg that, and we're done.
Sort of.
Sort of. Yeah, kind of. Yeah. All right. So z is going to equal x, xt minus 1, xt minus 2, xt minus 3, xt minus 4. Those are just our variables, our lag variables. Right? Advertising, last period's advertising, 2 period ago advertising, 3 period ago advertising, 4 period ago advertising. That's T0. ZT1 is going to be, again, it's still it's at lagged advertising, but it's 2 times 2 periods ago lagged advertising, 3 times 3 period ago, and then 4 times 4 periods ago. And then ZT2 is going to be kind of the same structure as ZT1, except we're going to square this. It's going to be 2 times 2 squared, 2 period advertising, 2 periods ago advertising, 3 squared, 3 periods ago, 4 squared, 4 periods ago. And again, we do the math, and that'll come out to 4, 9, 16. And ZT3 is going to have a similar thing, except it's going to, instead of squaring it, we're going to cube it. Cube this one, cube that one, and we're going to get that. All right, I'm just going to bring those other 2 over there since they're kind of by themselves. Okay. This is your estimating equation. Once we define those z's, then we have, in essence, constant, and then we're going to, we've already defined zt to be that, ZT1 could be that, ZT2 could be that, and ZT3 to be that. And this is what we run in Stata after we've defined. So we haven't used Stata at all. Well, actually, we haven't used Stata at all. We haven't estimated anything. So this is the regression we're going to run. And this will give us, remember this is a cubic, so this will give us our cubic polynomial. Is that as bad as I said it was?
Worse.
Worse?
It's a long way. But how is the distributed lag model tied to that?
Through kind of all the way back. So through the x's. So here's our lags, right? So these are still our lags, but we've got this mathematical structure where these are being cubed, squared, and then just the coefficients there. And this is a cubic. This isn't a quadratic. I just thought, okay, we can see the pattern kind of for a cubic. The quadratic will be a little bit easier. So we estimate that. And let's go back. Because we only have right, 1, 2, 3, 4 coefficients, it essentially reduces the number of coefficients we have to be collinear. So it reduces the effects of multicollinearity, which is one of the reasons we're worried about. We're concerned about those unrestricted distributed lag models. And let's see, how does polynomial language? Okay, we'll just go over that. Yeah, it just reduces the number of coefficients we're going to estimate. So imagine if this was a 8 or 6 period lag. It would still boil down to those 4 coefficients. All right, so let's do this again. This is the one we're going to run. Not necessarily the 8 period lag, but we're going to run a second degree polynomial. That's going to give us this equation, this picture. And again, we don't know how many lags there's going to be. All right. If r equals 2, our quadratic, and lag length is going to be 8, then we're going to have each coefficient take the form of that. And that's that quadratic form. And it looks like this, right? C, B, and then A, x squared. Oops. All right. So the coefficient on betas for the 0 lag is again 0 to the 1, 0 to the 2, so we end up with gamma 0. The coefficient on the 1 period lag becomes again 1 to the 1, 1 to the 2. Coefficient on the 2 period lag, 2 to the 1, 2 to the 2. On the 3 period lag, 3 to the 1, 3 to the 2. 4th period lag, 5th period, 6th period, 8 periods. And you can see that pattern here where we got 1, 2, 3, 4, 5, and then this is going to be 1, 4, 9. It's going to basically be b squared, right?
So this second degree polynomial is going to give us that curve.
Yep.
So we're only ever going to need 3 coefficients, well, the 3 parts of the equation that
Yep.
line up with the betas to get that. Okay.
Yeah. So the other one was a cubic, and we're not going to do that. I just kind of did that to give you an idea of there's a kind of a pattern going on here. Okay. So we take these, and we substitute them into the original equation. So those are the same things, I just rewrote them. Typed them. So there they are. We substitute these into the original unrestricted distributed lag model. And you're going to get some pretty nasty looking stuff. All right, that's relatively easy. Messy but easy. All right, then we're going to construct those z variables. And remember, we want essentially this three-piece model: constant, x, and x squared. Construct the z. So remember, it's an 8-period lag model. So the zt0 is going to be xt advertising all the way to the 8-period lagged advertising. zt1, remember it starts at xt minus 1 and then goes 2, 3, 4, 5, 6, 7, and 8-period lags. And again, the lag, the lag length is the actual coefficient on that lag. So for the 2-period lag, the coefficient on it is 2. 3-period lag, the coefficient is, and then for this one, we're going to square those. So notice, that's why I kind of put them below each other, that the 4 is 2 squared, 9 is 3 squared, 16 is 4 squared, and so on. Then we estimate that model. So instead of, remember we have an 8-period lag model, instead of having 8 coefficients, instead of having 9 actually, so having advertising all the way to 8-period lagged advertising, we've only got 3. And what that does, remember, multicollinearity results from you having a bunch of independent variables that are highly correlated. Because we only have a few independent variables, basically zt0, zt1, and zt2, because we only have those 3 variables, we eliminate the possibility of multicollinearity. So we're going to be much more confident in these results than we were in the unrestricted lag coefficients model. And this gives you the gammas. So we're going to want, so once we estimate this, our coefficient, our regression coefficients are going to be gamma 0, gamma 1, gamma 2. Then we're going to go back to that first page, that first slide, and we're going to replug these back in. So remember on the problems that we just did, we had to pull the coefficient. Now we're going to pull that coefficient, that's going to be beta 0. We're going to pull that coefficient from zt0, add it to the coefficient from zt1, and add that to the coefficient of zt2. We're going to pull those coefficients, but now we're going to multiply them times 2 and 4, and then multiply them times 3 and 9, and then 4 and 16, 5 and 25, and so on. And this is just math, right? This is part of that do file we're going to have to construct.
You're pulling the coefficients
From the regression output, yeah. Exactly, I'm pulling them from the regression output of this regression. Oops, let's not do that. Infinite is, is next. All right, let's take a look and see what happens. Let's actually do it. So any questions? I'll leave this. So what data set is this? This is problem set 2. Let's do this one, which is...
So are we using the same data set?
This is a different data set.
I mean, for our homework, are we using the same one, or is it?
This is a different data set.
Okay.
For the homework, we're going to use a different data. And the reason why is when you did yours, you said it looked different than mine, but did it still kind of look jaggedy like that?
Oh, it was jaggedy,
Yeah.
yeah, it's not
So-
the same shape.
So that's fine, you got close to what we needed. This doesn't look like that though, right?
No.
Exactly.
If I had fallen into that, I'd be a genius.
Yeah,
No,
so that's why we're not gonna use the same data set that we just finished for this one. This one looks actually more like the geometric decay. So we're gonna be able to smooth this out and get that nice geometric decay. All right, so this is the data set, what this data set looks like. T, I had to anonymize this again with, take away the years. They wouldn't even let me know what years or periods or anything else. Or I should say they didn't want anyone to know what years or periods. All right, so we got an undistributed lag model. So this is what we did last time. Here's an 8-period lag model. We can see that first two, initial advertising is not really significant. Is not significant. Neither is the 1 period, but then 2 periods ago, advertising has an effect, and 3 periods ago, and then 4 periods ago, marginally, but not 5, 6, 7, but 8 periods ago, I remember all of a sudden. So again, kind of classic signs of multicollinearity is you get jumbled results. That's the problem with these. And believe me, I've heard people sit and try to explain away, oh yeah, it makes perfect sense that you remember something from 8 periods as opposed to 7, 6, and 5 periods ago. But 4 periods ago, you listen to these people try to make sense of this when the answer is, we know these are just imprecise estimates and we shouldn't put too much stock in the picture that they produce instead of sitting around making stuff up. Okay, so we can run that. We can graph this also. And we're going to graph this the same way we graphed it before. Generate a lag variable, pull those coefficients out, and then graph. Right? Okay. That looks like a bubble. It starts out slow, it peaks. You know, this is kind of strange, but what do we think is causing this?
Big gap.
No,
No.
this doesn't have a gap. So again, we get a nice picture except for that thing at the end. What do we think is causing that? That thing that we keep referring to.
Collinear.
Multicollinearity, yeah. So it looks like a bubble except for that wacky. Again, what we're saying is the effect of advertising is relatively slow. Initial advertising has a small impact, but then it gradually builds up. It peaks and then starts to die out. And then 8 periods later, we all of a sudden remember whatever happened 8 days ago or 8 months ago or 8 whatever periods ago. Again, it doesn't make any sense. We don't want to have to sit and explain away this tail here. It's probably, again, an imprecisely estimated coefficient. We can deal with that. But that looks pretty close to a bubble to me. What we're going to do is say, look, let's just make it look like a bubble. We think it's a bubble. Let's force it to look like a bubble. And that's what Shirley Ullman did. She's going to impose some structure on that so that it looks more reasonable. And that's what we're going to do. All right, now we got to go to that. Let's go back 1 second. All right, we're going to do a polynomial lag. I'm sorry, quadratic lag. All right. Did I use 8 periods? Is that my 8 periods? Yeah, it was. So this just so happens to be 8 periods also. So we need to go through all this stuff. Again, it's a quadratic, so it's a fairly simple form. Then we just got to kind of do the math here. Take those, goes into that. So let's see what handy dandy do file says. In essence, we can skip a lot of this because in the end, all we're going to estimate is the z equation. So as long as we know the form of the z equation, we're fine. And what is the form of the z equation? Remember, x is still just x, which is advertising. And we need to take, we need to construct this. So advertising, lagged advertising, 2-period, and so on. ZT1 is we're just going to multiply 2-period lagged advertising by 2, 3-period lagged advertising by 3, 4-period lagged advertising by 4. ZT2, we're going to go this square, 2 squared, so it's going to be 4, it's going to be 9, 16, 25. So we just need to construct these z variables. So all that other stuff just tells us how we got to here, but for us, the practicality of implementing this, all we got to do is construct those z variables. Make sense? All right, so let's do it. Go. So, let's see if this makes sense. Advertising, XT, right? Lagged advertising, L1 dot advertising, lagged advertising. 2-period lagged advertising, 3-period lagged advertising, all the way to 8-period lagged advertising. Then we construct ZT1. It's the same thing. So essentially I can copy this, paste it, delete the current one, and then I've got lagged advertising. And for the 2-period lagged advertising, I multiply that by 2. For the 3-period lagged advertising, I multiply that by 3. For the 4-period lagged advertising, I multiply by 4, and so on and so on.